Insertion sort.
Insertion sort is a simple sorting algorithm that builds the final sorted array one item at a time. It is much less efficient on large lists than more advanced algorithms such as quicksort, heapsort, or merge sort. However, insertion sort provides several advantages. Simple implementation, efficient for quite small data sets, adaptive, that is, efficient for data sets that are already substantially sorted. The time complexity is O(n plus d, where d is the number of inversions, more efficient in practice than most other simple quadratic, that is, O(n)2 algorithms such as selection sort or bubble sort. The best case, nearly sorted input, is O(n) stable. That is, does not change the relative order of elements with equal keys in place. That is, only requires a constant amount O(1) of additional memory space, online. That is, can sort a list as it receives it. When humans manually sort something, for example, a deck of playing cards, most use a method that is similar to insertion sort.
Algorithm.
Insertion sort iterates, consuming one input element each repetition, and growing a sorted output list. Each iteration, insertion sort removes one element from the input data, finds the location it belongs within the sorted list, and inserts it there. It repeats until no input elements remain. Sorting is typically done in place, by iterating up the array, growing the sorted list behind it. At each array position, it checks the value there against the largest value in the sorted list, which happens to be next to it, in the previous array position checked. If larger, it leaves the element in place and moves to the next. If smaller, it finds the correct position within the sorted list, shifts all the larger values up to make a space, and inserts into that correct position. The resulting array after k iterations has the property where the first k+1 entries are sorted, +1, because the first entry is skipped. In each iteration the first remaining entry of the inputs is removed, and inserted into the result at the correct position, thus extending the result. Becomes. With each element greater than x copied to the right as it is compared against x. The most common variant of insertion sort, which operates on arrays, can be described as follows. Suppose there exists a function called insert designed to insert a value into a sorted sequence at the beginning of an array. It operates by beginning at the end of the sequence and shifting each element one place to the right until a suitable position is found for the new element. The function has the side effect of overwriting the value stored immediately after the sorted sequence in the array. To perform an insertion sort, begin at the leftmost element of the array and invoke insert to insert each element encountered into its correct position. The ordered sequence into which the element is inserted is stored at the beginning of the array in the set of indices already examined. Each insertion overwrites a single value, the value being inserted. Pseudocode of the complete algorithm follows, where the arrays are 0-116. The outer loop runs over all the elements except the first one, because the single element prefix a is trivially sorted. So the invariant that the first i+1 entries are sorted is true from the start. The inner loop moves element a to its correct place so that after the loop, the first i+2 elements are sorted. After expanding the swap operation in place as t, a, t, where t is a temporary variable, a slightly faster version can be produced that moves a to its position in one go and only performs one assignment in the inner loop body 116. The new inner loop shifts elements to the right to clear a spot for x equals a. Note that although the common practice is to implement in place, which requires checking the elements in order, the order of checking, and removing, input elements is actually arbitrary. The choice can be made using almost any pattern, as long as all input elements are eventually checked, and removed from the input.
Best, worst, and average cases.
The best case input is an array that is already sorted. In this case insertion sort has a linear running time, that is, n. During each iteration, the first remaining element of the inputs is only compared with the rightmost element of the sorted subsection of the array. The simplest worst-case input is an array sorted in reverse order. The set of all worst-case inputs consists of all arrays where each element is the smallest or second smallest of the elements before it. In these cases, every iteration of the inner loop will scan and shift the entire sorted subsection of the array before inserting the next element. This gives insertion sort a quadratic running time, that is, O(n)(2). The average case is also quadratic, which makes insertion sort impractical for sorting large arrays. However, insertion sort is one of the fastest algorithms for sorting very small arrays, even faster than quicksort. Indeed, good quicksort implementations use insertion sort for arrays smaller than a certain threshold, also when arising as subproblems. The exact threshold must be determined experimentally and depends on the machine, but is commonly around 10. Example: the following table shows the steps for sorting the sequence 3, 7, 4, 9, 5, 2, 6, 1. In each step, the key under consideration is underlined. The key that was moved, or left in place because it was biggest yet considered, in the previous step is shown in bold. 374952661 374952661 374952661 347952661 347952661 345792661 234579661 2345671 1234567
Relation to other sorting algorithms.
Insertion sort is very similar to selection sort. As in selection sort, after k passes through the array, the first k elements are in sorted order. For selection sort these are the k smallest elements, while in insertion sort they are whatever the first k elements were in the unsorted array. Insertion sort's advantage is that it only scans as many elements as needed to determine the correct location of the k plus first element, while selection sort must scan all remaining elements to find the absolute smallest element. Calculations show that insertion sort will usually perform about half as many comparisons as selection sort. Assuming the k plus first element's rank is random, insertion sort will on average require shifting half of the previous k elements, while selection sort always requires scanning all unplaced elements. If the input array is reverse sorted, insertion sort performs as many comparisons as selection sort. If the input array is already sorted, insertion sort performs as few as n1 comparisons, thus making insertion sort more efficient when given sorted or nearly sorted arrays. While insertion sort typically makes fewer comparisons than selection sort, it requires more writes because the inner loop can require shifting large sections of the sorted portion of the array. In general, insertion sort will write to the array O(n)(2) times, whereas selection sort will write only O(n) times. For this reason selection sort may be preferable in cases where writing to memory is significantly more expensive than reading, such as with the EEPROM or flash memory. Some divide-and-conquer algorithms such as quicksort and merge sort by recursively dividing the list into smaller sublists which are then sorted. A useful optimization in practice for these algorithms is to use insertion sort for sorting small sublists, where insertion sort outperforms these more complex algorithms. The size of list for which insertion sort has the advantage varies by environment and implementation, but is typically between 8 and 20 elements. A variant of this scheme runs quicksort with a constant cutoff k, then runs a single insertion sort on the final array. This preserves the O(n)(lgn) expected time complexity of standard quicksort, because after running the quicksort procedure, the array A will be partially sorted in the sense that each element is at most k positions away from its final, sorted position. On such a partially sorted array, insertion sort will run at most k iterations of its inner loop, which is run n1 times, so it has linear time complexity 121.
Variants.
DL Shell made substantial improvements to the algorithm. The modified version is called shell sort. The sorting algorithm compares elements separated by a distance that decreases on each pass. Shell sort has distinctly improved running times in practical work, with two simple variants requiring n3/2 and n4/3 running time. If the cost of comparisons exceeds the cost of swaps, as is the case for example with string keys stored by reference or with human interaction, such as choosing one of a pair displayed side by side, then using binary insertion sort may yield better performance. Binary insertion sort employs a binary search to determine the correct location to insert new elements, and therefore performs log2, n comparisons in the worst case, which is and log n. The algorithm as a whole still has a running time of n2, on average because of the series of swaps required for each insertion. The number of swaps can be reduced by calculating the position of multiple elements before moving them. For example, if the target position of two elements is calculated before they are moved into the right position, the number of swaps can be reduced by about 25% for random data. In the extreme case, this variant works similar to merge sort. To avoid having to make a series of swaps for each insertion, the input could be stored in a linked list, which allows elements to be spliced in or out of the list in constant time when the position in the list is known. However, searching a linked list requires sequentially following the links to the desired position. A linked list does not have random access, so it cannot use a faster method such as binary search. Therefore, the running time required for searching is n, and the time for sorting is n2. If a more sophisticated data structure, for example, heap or binary tree, is used, the time required for searching and insertion can be reduced significantly. This is the essence of heap sort and binary tree sort. In 2004 Bender, Farag Colton, and Mostero published a new variant of insertion sort called library sort or gapped insertion sort that leaves a small number of unused spaces, that is, gaps spread throughout the array. The benefit is that insertions need only shift elements over until a gap is reached. The authors show that this sorting algorithm runs with high probability in and log n time. If a skip list is used, the insertion time is brought down to log n, and swaps are not needed because the skip list is implemented on a linked list structure. The final running time for insertion would be and log n. List insertion sort is a variant of insertion sort. It reduces the number of movements.
List insertion sort code in C.
If the items are stored in a linked list, then the list can be sorted with 1 additional space. The algorithm starts with an initially empty, and therefore trivially sorted, list. The input items are taken off the list one at a time, and then inserted in the proper place in the sorted list. When the input list is empty, the sorted list has the desired result. The algorithm below uses a trailing pointer for the insertion into the sorted list. A simpler recursive method rebuilds the list each time, rather than splicing, and can use n stack space.